Buckle up, everyone, because we're going to talk about Furstenberg's proof of the infinitude of the primes, which is a topological proof of the fact that there are infinitely many prime numbers. The first step is to define a topology on the integers, and we're going to use what's sometimes called the evenly spaced topology, or what number theorists called the profinite topology of the integers. Some notation first. For a and m integers, a plus m times z is going to denote the arithmetic progression, that is a plus any multiple of m. So for example, if p is a prime, p times z denotes all the integer multiples of the prime p. Here's the profinite topology of the integers. A subset u of the integers is open if and only if every element of u sits inside some arithmetic progression fully contained in u, or u is the empty set. Notice that in particular, if u is not empty, then u has to be infinite because it contains an infinite arithmetic progression. Some properties of this topology, like we just saw, if u is open and u is not the empty set, then u is infinite. In particular, if u is finite, then u cannot be open. Second, an arithmetic progression is itself an open set, but an arithmetic progression is also closed, because if you take all the possible residues when you divide modulo m and you add up all these arithmetic progressions, then you get all of the integers. So for example, that one is open, but the union of these finitely many open sets is also open, so the complement, this one, is closed. So an arithmetic progression is opened and also closed. Okay, then we're ready for our proof. Suppose for a contradiction that there are only finitely many prime numbers. Then the union over primes of the multiples of p, that is a finite union, and since each one of those is closed, the union of finitely many closed sets is closed. So this is closed. But now notice that any integer that is not plus or minus 1 is divisible by a prime number. So this has to be the union of all the multiples of a prime as we run over all the prime numbers. So we get this equation. But remember that we are assuming there are only finitely many prime numbers, and the union of finitely many closed sets is closed. On the other hand, the set with just the numbers plus or minus 1 is finite, and therefore it cannot be an open set in this topology, which means that the complement cannot be closed. But this set, which is not closed, is closed, so we've reached the contradiction, and that's the end of the proof. And the really cool part is that this very complicated proof is just Euclid's proof of the infinitude of the primes in some topological language.